Okay, today I'm gonna review about the DRAM process. And first is the memory accuracy. CPU register and cache and DRAM. It going down, we can make improvement. We can make improve the integration. So the lowest sector is what we used in the device for USB and SSD like that. And then this structure is it operated by the bit. So the bit is controlled by the structure of a DRAM. So first, what is the DRAM? It it can make one transistor. It made by one transistor and one capacitor. And this is it's a characteristic in, in random access memory. So we should have to refresh this DRAM to to sustain the data is useful because the characteristic about the capacitor, the time goes long and capacitor make it discharging. So we solve this problem, we should have to refresh process. And then this is the DRAM structure. It used the one cap transistor and one capacitor. And this is the word line and bit line. Word line connected by the gate, so it can work as a switch function and on-off operation in transistor. And then the bit line is control the data, 0 or 1. So you can connect by the source. And last, the capacitor, it means the storage node. So this is connect to the drain. This is the basic structure about the DRAM. And then these two types of the DRAM structure. So this is the cross-sectional view about the DRAM. First is a trench structure. The capacitor, it made by the trench process. So this is capacitor and this is the transistor. This distance is just too long, so it can get a better summer budget. And then the stack structure about the DRAM, it can transistor and capacitor in here. So this is the processor issue is occurred, so it can much less summer budget than the trans structure. And then the capacitor is the most important thing about the DRAM. So we can prevent the discharge. We can improve the cap to the epsilon, the thickness and area. We can use the improve the area and improve the epsilon. When we improve the epsilon, we can use the high K method to the dielectric and improve the area. We can improve the process about the make it area. And then this is the DRAM layout. The DRAM used in the array, used in the shape about array. So you can see this, the gate as drain and source. First, I told you the source is going to bit line and the gate was the word line and the storage node to the connected by the drain. So this is the top view about this layout about the one cell. You can see the drain and source and drain. These the figures point is we use the source in the common. We share the two cell about the source. Why we should have to do that? Because we should have to improve the integration about the DRAM and improve the integration. It means the much more capacitance about the data. So I told you before this shape about the rumbling thing, we want to make it this shape because this shape improve the area sector. And then we can use the high K method in this section. We can should improve the epsilon, so we can make a better capacitance. And there's a 8 F-squared shape and 6 F-squared shape. We define the unit cell about the 8 F-squared. The width is the 4 Fs and the length is 2 Fs. But this area is much bigger than we needed. So we should reduce this area. So we can remove the passing gate area. So the result is the 6 F-squared. How we remove the passing gate area? You can see this figure. This is the 8 F-squared and this is the 6 F-squared. We can tilt the active area so we can make it much smaller area unit cell. So now it's much better than 6 F, much better than 8 F-squared, but this process is very challenging. And then you can see this top view about the DRAM. The left is the 8 F-squared, then right is the 6 F-squared. You can see this much more integration is better than 8 F-squared. And cell array transistor. We can use this array structure. The cell array transistor is occurred. The much more improved the integration. We should have to devise the scaling down. So it make the channel length is going shorter. It may occur the short channel effect. So we use the shape of the channel to shift to the recess like this, and the drain is like this. It make a much more gate length, so we solve this problem. Not quite, not a quite, but and then the scaling down is going much smaller. It can make also occur the problem SCE. So you can use the channel shape like this. This is a SR cat. And then this SR cat is not much enough to solve this problem. So we use it looks like the channel shape is a saddle. So we can use the code is the shadow fin process. It can make a better substrate string and deeper effect than the recess FinFET. So currently we use the saddle fin to the cell array transistor. And then in the DRAM cell, we use the spin to the going to the body, but there is a limit is it has come, so we use the spin going up. It's just like a filler. In the filler and source and drain and bit line what line is a more into the filler. So we can see this the 8f squared is it their unit cell area is much bigger than the 6f squared, and then the much smaller than 6f squared is the 4f squared. This pillar, we can call this the particular pillar transistor. This is the total. This is the total thing about the Dram cell array, and this time we got okay. I'm gonna over about the session, and thank you.